Hello students, welcome to Sri Chandra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 6 of a unit moving charges and magnetism. In today's class we are going to discuss about the applications of Biot-Savart law. In the previous class we were discussing with the Biot-Savart's law with circular charged arc on its axis and on its center. So let's just revise the previous class. Let's just revise it very quickly and we will move with the applications of this. We have discussed that if a circular ring is there and you require a magnetic field on its axis at point X, then the magnetic field at point P could be written as mu naught into IR square divided by 2 into bracket R square plus X square to the power 3 by 2, where R was the radius of the ring and X is the perpendicular distance from the center of ring to point P. Yes, then we were discussing with the certain cases that if in this situation, if X was 0, that means at the center, if I required a magnetic field at the center, let's just put the value of X equals to 0 and the magnetic field could be given. A magnetic field could be written as mu naught I by 2R. If X is much less than R, then using the principle of binomial theorem, I have written it, it's a mu naught I by 2R into bracket 1 minus 3 by 2 into bracket X square by R square. And the next case is where if X is much greater than R, that means it is very far away from the ring, then it could be written as that as R is much smaller as compared to X. That's why I can ignore the R when I'm going to add it or I'm going to subtract it. So it's a mu naught IR square by 2 into X cube. And last but very important, it's a magnetic field due to charged arc on its center. That this was the charged arc and current flowing through this arc is I, and you require a magnetic field at point P, and this angle is theta and the radius is R. So what you can have, it's a B at P, magnetic field at P is equals to mu naught I by 2R multiplied by theta by 2 pi. And to find out the direction, you understood that if current is in clockwise direction, then magnetic field at point P is inside the plane, that we denote it by a cross. And if current is in anti-clockwise direction, then magnetic field is outside the plane, which is outside the plane. I hope these things are clear. Is it clear? Is it? Yes. So this is the points we were discussing in the last class, and now let's begin with the numericals of this session. So one thing, please have your pen and paper with you. Do questions as fast as possible, and you are not just going to watch it, you are going to attempt it with me. Yes, and at the end of each slide we are going to discuss about the answers. Yes, so let's begin. All the best, guys. Now let's have a look to the question, what it is saying. It says that two identical coils have a common center and their planes are at angles to each other, carry equal currents. Okay, if the magnitude of the induction field, yes, this is magnetic field, at the center due to one of the coil is B, then the resultant magnetic induction field due to this combination. So go through the data one more time if you don't understand what he or she wants to ask. Go through it very carefully, because a rough sketch of the situation must be drawn. If it is there, this numerical is very easy. If it is not, you might not get a feeling of it. So what does it say? It says two identical coils are there. They are having a common center and their planes are at angles to each other. The planes are at you can say perpendicular to each other. Yes, let's remove this. Their planes are at perpendicular to each other and they carry the equal currents. Now if the magnetic field due to one of the ring is B and you need to find out the resultant magnetic field. So the situation is something like this. Let's have a look. It is the first ring. Let's suppose this is its center and this is the second ring. Yes. So for the first ring, let's suppose current is flowing in this direction. This is I. And for the second ring, current, let's suppose it is moving in this direction. Yes, you require a magnetic field at point P. So if you understand this well, then this is the first, this is the second. So for the first ring, B1 is outside the plane. B1 is outside the plane. If I consider this ring, if I consider the first ring in the plane of your book, or let's say it's an XY plane, so B1 is outside the plane. And if you understand that this second ring, the second ring has been placed in the another plane, then this B2 is from, it is something like this. So B2 is in this direction. Yes, B1 it's a plus K cap, B2 it's a plus a J cap. I hope this is clear. Yes. Now what is B1? What is B1? As they said, they are identical. So it's a mu naught I by 2R into K cap. This is mu naught I by 2R into a J cap. Yes. What I want is, let's suppose this is I assumed K, this I assumed as a J. Yes, this is perpendicular to each other, so B net is equals to root of B1 square plus B2 square, as this 2 are same in magnitude, so this is root 2 into P. This could be written as root 2 times of mu naught I by 2R, and they have written mu naught I by 2R as a B, so root 2 times of B is the final answer. This is B net. I hope this is clear. What was your answer? Is it same? First, this is to be done. If you have rough sketch of it, you will get an answer. If you are not having it, it would be a difficult one to get it done. I hope this is clear. Is it clear? Are you sure? Great. So ready for the next question? Are you ready? Let's have a look. What does it all about? It's a circular coil of radius 25 centimeter carries a current of 50 amperes. If it has 35 turns, the flux density at the center of the coil. So for singleton, what we are writing is B is equals to mu naught I by 2R. Yes, for n number of turns, the magnetic field at the center should be written as n multiplied by mu naught I by 2R, because all magnetic field will be going to add up, and when they are going to add up, the total magnetic field, or I should say a net magnetic field, will be the n times of magnetic field of singleton. So now what I need to do, I need to just put the value and get it done. It's n, which is equals to 35 turns multiplied by mu naught multiplied by I. Does it have I? Yes, it's a 50 ampere divided by 2 into radius. The radius, it's 25 centimeter, but it's a 20 centimeter, so it's 25 into 10 to the power minus of 2. I hope this is clear. So that should be is equals to 25 2s are 50. This is 35 multiplied by mu naught. It's a 4 pi into 10 to the power minus of 7 into 10 to the power minus of 2. Yes, mu naught is equals to 4 pi into 10 to the power minus of 7. And now get it done. It's 13 Tesla. I hope this is clear. Is it clear? Are you sure? Are you? Great. Let's work for the next question. what it is all about. It says a wire carrying a current of 140 ampere is bent into the form of a circle of radius 6 centimeter. The flux density at a distance of 8 centimeter, okay, on the axis passing through the center of the coil and perpendicular to its plane. Oh. So how should you do this? It is something like this, that this wire was there and it has been converted to a circle to of radius, it's a 6 centimeter. Now from this you need to find out a magnetic field at distance that is of 8 centimeter. This is that location. I hope this is clear. It's a point P. Yes, what do you want? You want a magnetic field at this point. So magnetic field at this point P could be written as mu naught I r square divided by 2 into bracket r square plus x square to the power 3 by 2. So this is equals to mu naught multiplied by I, 140 multiplied by radius r square, radius. It is 6 centimeter. So this is 36 into 10 to the power minus of 4. 36 into 10 to the power minus of 4. I hope this is clear. Is it? Yes. It's a 36 into 10 to the power minus of 4 divided by 2 into bracket r square. It's a 36 plus 64 into 10 to the power minus of 4 to the power 3 by 2. I hope this is clear. Yes. Is it? Is it clear? Is it clear? Yes. Okay, great. So now can you solve this? Can you solve this for certain Tesla? Yes. Yes. Only the mathematics has been left, and I'm sure you can do it very quickly. But did you understand the concept behind it? Do you? So can you do this kind of questions? Can you? Great. Let's work for the next question and do it quickly. You are doing good. Well done. Let's look for this question. It says two concentric circular coils A and B having radius 25 and 15 and carries a current of 10 ampere and 15 ampere. Now A has the 24 turns and B has 18 turns. The directions of the current are in opposite order. Okay, the magnetic induction at the common center of the coil. Okay, so what you need to do is that have a sketch of it. This is coil A and this is the center. This is coil B and they are having a common center. Yes, a coil A is having a current of 10 ampere and coil B is having a current of 15 ampere, but both are flowing in the opposite direction. So as I have made this in an anti-clockwise manner, this should be in a clockwise and this should be a 15 of ampere. Yes, number of turns of A it's a 24. Number of turns of B it's an 18. Yes. Now magnetic induction at the common center, it's a B1, that should be is equals to N1 multiplied by mu naught into I divided by 2R. So it's an N1 which is equals to 24 multiplied by mu naught into I, that is of 10 ampere divided by 2 into its radius. It's a 25 centimeter for first. Yes, this is 25 and this is 10. So this is 2 into 25 into 10 to the power minus of 2. Now B2, it's an N2 multiplied by mu naught I divided by 2R. N2, it's 18 turns multiplied by mu naught multiplied by current. It's a 15 of ampere divided by 2 into radius. radius, it's a 15 centimeter into 10 to the power minus of 2. I hope this is clear. Is it clear? Is it? So B1 could be written as, look at this, this is 10, this is 25 into 2, this is 10 5s are 50. So this is 24 by 5 into mu naught into 10 to the power minus of 2. So this B1 should be is equals to, it's a 24 by 5 multiplied by 24 by 5 into 10 to the power minus 2 into mu naught. This is B1. Now work for the B2. What is it? It's this is 18, this is 15. Okay, great. This 15 can gone, and this is 18 by 2, which is equals to 9 mu naught. This is 9 multiplied by 10 to the power 2 into mu naught. I hope this is clear. Now directions. B1, as this current is flowing in the anti-clockwise direction for the B1, so its magnetic field will be outside the plane. Second, it is flowing in the clockwise direction, so it is in the inside the plane. As both the directions are opposite to each other, so what you need to do is you need to have a subtraction, as B net is outside the plane, B second it's inside the plane, so B net should be is equals to B1 minus B2, something like this. Yes, put up the value and get it done for the Tesla. I hope this is clear. Is it clear? So is it fair enough to do this? Is it? Great. Let's work for the next question. What is it is? The question says that a coil of radius pi meters having 100 turns carries a current of 3 ampere. The magnetic induction at a point on its axis at a distance equals to root 3 times of its radius from its center. Yes, great. So what I need to do is that B is equals to, we understood this is n into mu naught I r square divided by 2 into root of r square plus x square to the power 3 by 2. This is our formula, and they says that it's a distance equals to root 3 times of its radius, so x3 is equals to root 3, x is equals to root 3 times of its radius, and the radius is pi, so this is root 3 times of pi. I hope this is clear. So let's just put up the value. The B, that is equals to mu naught, it's a 4 pi into 10 to the power minus of 7 multiplied by 100 of turns, it's a multiplied by 100 multiplied by current, it is having a current of 3 ampere multiplied by r square, this is pi square, divide by 2 into bracket r square, it's a pi square plus root 3 pi whole square to the power 3 by 2. Yes, if you observe this carefully, this is root 3 pi whole square, this is 3 pi square plus pi square, 3 pi square plus pi square, it's a 4 pi square, a square of it, it's a 16 pi r square, and then I need to find out the 3 by 2 power, that would be the 8 pi cube. This pi cube has been gone, and if I solve this, it's a 7.5 into 10 to the power minus of 6 Tesla, or Weber per meter square. It's a Weber per meter square. It is the unit that we have derived for magnetic field from the magnetic flux that you are going to learn in the next sessions. Yes, so it's a Weber per meter square. Even it is same as the Tesla. I hope this is clear. Is it? Great. Ready for the next question? Are you ready? Let's have a look. What does it says? It says that a long straight solid metal wire of radius 2 mm carries current uniformly distributed over its circular cross section, and the magnetic field induction at a distance of 2 mm from its axis is P, and the magnetic field induction at a distance of 1 mm. This is of Ampere circuital law. We are going to discuss it in the next session. So we are going to cover this in the next session. Yes, I will remember it. let's work for this question. So what does it say? It says that a circular ring of radius r, a circular ring of radius r carries a current I. The value of B along its axis at a distance r from its center. So this is the situation. This is r and current I is flowing through it along its axis at a distance r from its center. So magnetic field at point P, it is mu naught I r square divided by 2 into bracket r square plus x square to the power 3 by 2. This is equals to mu naught multiplied by I multiplied by r square divided by 2 into r square plus r square to the power 3 by 2. So this is equals to mu naught I r square divided by 2 into r square plus r square. It's a 2r square to the power 3 by 2. I hope this is clear. Is it? Is it clear? Yes. Are you sure? Yes, this is magnetic field at B is equals to mu naught I r square upon 2 into 2r square to the power 3 by 2. So this is equals to mu naught I r square divided by 2 into 2 to the power 3 by 2 multiplied by r to the power cube. So here it's a r square, it's a r cube, so one term has been replaced. It's a mu naught I by r, and this is 2 to the power 3 by 2. So this is equals to 2 to the power 1 plus 3 by 2. It's a 5 by 2. Yes, this would be the answer. Or even if you wish, you can do it as 2 into 2 to the power 3 by 2. This is 2 into 2 into 2 to the power half. Yes, it is the same thing, 1 plus half. So this is 4 of root 2 according to the answer. Yes, it's a mu naught I divided by 4 root 2 multiplied by r. This is magnetic field at point P. Yes, did it? Got the answer? Or got the correct answer? Are you sure? Well done. Let's work for the next question. Do it quickly. What does it say? An infinite long straight wire is bent into a semicircle of radius r as shown in the figure. A current I is sent through the conductor. The magnetic field at the center of the semicircle, this is where you required. So what you need to do is that I amount of current is entering, I amount of current is leaving. Name the segments. This is the first segment. This circular or semicircle ring is the second segment. This is the third segment. So for the first segment, it is the situation. Yes. So this is the case where theta equals to 0. So B1 equals to 0. For the third, this is the situation. Yes. Again, theta is equals to 0. So B3 equals to 0. Now I have been left with the second segment. So for the second segment, it's a B2, which should be is equals to mu naught I by 2r multiplied by theta by 2 pi. As it's a semicircle ring, it's a mu naught I by 2r multiplied by pi by 2 pi. This is half. It's a mu naught I by 2 2s are 4r. That's it. This is the answer. So this magnetic field B net, this magnetic field would be given as mu naught I divided by 4 into r. That's it. Yes, where it is inside the plane or outside the plane. Yes, it is inside the plane because current is flowing in the clockwise direction. As current is flowing in the clockwise direction, it is inside the plane. Is it clear? Is it? Is it? Great. Have a look to this question. Very good question. Have a look. It's a magnetic field they require at the center of circular lip in the circuit shown below. Yes, this is the center, and let's assume that this is distance r. It's a radius for the circle, as well as it is the distance for the wire. Let's assume that current I is entering and current I is leaving, something like this. So what you need to do is that consider this segment as a first, this segment as a second, and this circle as a third. Yes, it has been coming from the infinite and it is leaving to the infinite. So for the first segment, the situation is, it is somewhat like semi-infinite wire. This is R and this is the I that is coming. So from on this side, alpha should be equals to 90 degree and beta should be equals to 0 degree. So this B1 should be equals to mu naught I by 4 pi R into bracket sine of 90 degree plus sine of 0 degree. Yes, and when it is sine of 90 degree plus sine of 0 degree, this should be written as mu naught I by 4 pi R multiplied by sine 0 would be a 0. This is mu naught I by 4 pi R. What would be the direction? Using right hand palm rule you can find it out, as well as you can make this as an imaginary circular loop and get it done. So whatever you do, but it would be the outside the plane of the paper. So this will be like this. Now what would be the situation with the second segment? It is same, almost same. Yes, this is the point P where magnetic field is required. This is, for this, alpha is equals to 90, alpha is equals to 0 degree and 1 minute. Yes, alpha is equals to 0 degree and beta is equals to 90 degree. So it is even the same, that magnetic field due to second segment, it's a mu naught I by 4 pi R multiplied by sine 0 degree plus sine 90 degree. The sine 0, a sine 0 would be a 0, sine 90 would be a 1. It's a mu naught I by 4 pi R. Yes, even for this situation, it is the outside the plane. So this is the magnetic field due to B1 and B2. Now I need to find out the magnetic field due to circle. It is something like this. I is entering, I is moving through the circle, and I is leaving. You require magnetic field at this point. This is radius R. So B1 equals to mu naught I by 4 pi R, that is equals to B2, and both are in outside the plane. Now let's work for the circular segment. The circular segment is the third one. So B3 it is equals to mu naught I by 2R. Now direction of it, as you can see, the current is flowing in the clockwise direction, and as it is moving in the clockwise direction, the magnetic field will be the inside the plane. So this B net would be equals to, I'm going to add this 2 because they are having the same direction, and I'm going to subtract it from this. It's a B1 plus B2 minus of B3. So this would be equals to mu naught I by 4 pi R multiplied by 2 minus mu naught I by 2R. This has gone, and so B net could be written as, it's a mu naught I by 2R into bracket, the pi will remain, it's a 1 by pi minus of 1. So that should be mu naught I by 2R into bracket 1 minus pi divided by pi. I hope this is clear. Is it clear? Is it clear? Great. So can you do this kind of questions? What was your answer? Is it same? Yes. If you want to match it, if you want to match it with the answers, so look at this. Every time 4 pi is there. So what you can do is to make this a 4 pi, you need to multiply it and you need to divide it with 2 pi. So this is equals to, in this situation, mu naught I divide by 2 into 2 pi. It's a 4 pi r. Yes. Then 1 by pi minus of pi into bracket 2 pi. Then cancel this and try to reach as the options. I hope this is clear. Yes. So what you need to do is, every time you need to go for the magnetic field, that means a value of a magnetic field, we are talking about the magnitude of magnetic field, then go for the directions, then just do the same thing every time, and calculate the net magnetic field. Yes, once you get the net magnetic field, yes, arrange your answer according to the options given. Yes, and that can be done by trial and error. Yes, so let's work for the next question. What is it? The question says that in the given figure, the magnetic induction at point O. Yes, this is required. So what you are supposed to do, give the number. It's the first segment, this is second segment, and from this to this is the third segment. Yes, so what would be the magnetic field for the first segment? The situation is something like this. It is, and at this point it is required. So in this case theta is equals to 0 degree, and if theta is equals to 0 degree, magnetic field at this point, they have denoted it as an O. It's a 0 because theta is 0. Now let's work for the second segment. It's a semicircular arc, so magnetic field would be mu naught I by 2r into theta, which is pi by 2 pi. This is equals to mu naught I by 4r. Yes, in which direction it is? As current is flowing in the anticlockwise direction. So magnetic field is up perpendicular and outside the plane. It's a mu naught I by 4r outside the plane. Yes. Now let's work for the third segment. It is something like this, that this current I is flowing through here. This is the point where magnetic field is required. This is the distance r because this is the radius. Yes, it's a semi-infinite wire, and when it's a semi-infinite wire, angle over here, it's a, let's assume it's a beta is 90 degree, alpha is 0 degree. So for the third segment, magnetic field at P, it is equals to, magnetic field at P, it's a mu naught I by 4 pi r multiplied by sine of 90 degree plus sine of 0 degree. That would be is equals to, this is 1, this is 0, so that would be mu naught I by 4 pi r. Correct? Great. So now let's just find out the direction. Yes, even if you bend this in a circular loop, you can see this, that it is, the current is moving in the anticlockwise direction, and when it is moving in the anticlockwise direction, magnetic field is outside the plane. Even you can use the right hand palm rule, so go with the right hand palm rule, and you will find that magnetic field is outside the circle. Oh sorry, it is outside the plane of the circle. So here both the magnetic field B net should be equals to P1 plus P2 plus B3. As I know, B1 is 0, B2 it's a mu naught I by 4r, and B3 it's a mu naught I by 4 pi r. Yes, first it's a mu naught I by 4r and mu naught I by 4 pi r, both are outside the circle, so that could be written as mu naught I by 4r as a common. It's a 1 plus 1 by pi, and rest of the thing you can do it outside the plane of the paper. Is that clear? this is outside the plane of the paper. Is it clear? Are you sure? So will you be able to solve this kind of questions? Will you be ready for the next question? Let's have a look. What does it say? It says that two concentric circular conductors of radius r and 2r are lying on a plane and they carry equal currents in the same direction. Correct. If the magnetic field due to inner conductor is 1 Tesla at its center, the resultant magnetic field due to the two conductors at its center that is required. Okay, so how can I do this? That says that let's say this is the one of the circle, this is the second circle, radius here, this is r, and another it's a 2r. They carry equal current in the same direction. Let's assume it as an anti-clockwise direction, I, and the current would be the same. So the magnetic field is equals to mu naught I by 2r. As the current would be the same, I can write like this. It's a B directly proportional to the 1 by 2. Now let's just find out, because I know the value of the magnetic field B1, so I need to find out the second one. It's B1 is to B2, and thus if I put up, it's the ratio of the radius, it's R2 is to R1, and if it's an R2 is to R1, this B1 is to B2 would be equals to 2. So B2, a second calls magnetic field, it's a 1 by 2. Now as they said that the current is flowing in the same direction, so it's a B1 plus B2, and this could be done at a 1 plus half. This is equals to 1.5 Tesla. I hope this is clear. Is it great? Now I want to make one correction to the question, and you are going to do this. That in the previous question, if current is moving in opposite directions, if current is flowing in opposite directions, then find net magnetic field. Yes, you need to do it on your own. Please do it. Try yourself. Yes, your answer should be zero point 0.5 Tesla. I hope this is clear. Is it clear? Is it great? So shall we move to the next question? Shall we? Let's have a look. It says that 2 points P and Q are on the axis at a distance of r and 3r from the center of a circular coil of radius r. Okay, and carrying a current. The ratio of the magnetic inductions at point P and at point Q. Yes. This is the circular coil, and this is having radius of r. One of the 2 points P and Q, that let's suppose this is point P and this is at a distance of r. So let's just calculate this. It's a BP, that should be is equals to mu naught I r square divided by 2 into bracket r square plus x square. Here x is equals to r to the power 3 by 2. That should be is equals to mu naught I r square divided by 2 into r square plus r square. This is r square plus r square. This is 2r square. So this is 2 to the power 3 by 2 multiplied by r cube. Yes, this is r square, this is r cube. So this is equals to mu naught I divided by 2 into 2 to the power 3 by 2 into r. Yes, because this is r square, this is r cube. Now, a same way, on the same manner, let's just try to assume, try to get it done. This is point, this is radius r, and you want it at the location of 3r. This is point q. So magnetic field at point q, that could be written as mu naught into I to r square divided by 2 into bracket, divide by 2 into bracket r square plus it's a 3r, it's a 9r square to the power 3 by 2. This is equals to mu naught I r square divided by 2 into r square plus 9r square. It's a 10r square. So this is 10 to the power 3 by 2 multiplied by r cube. This is equals to mu naught I by 2 into 10 to the power 3 by 2 multiplied by 1 by r. Yes, this is magnetic field at point Q. I hope this is clear. So if I take a ratio of this, if I want to take a ratio of this, let's have a look that magnetic field at P and magnetic field at Q. This mu naught I are equal, that are going to cancel. This 2 into R is equal, so this 2 into R is cancel. So if I take a magnetic field, I need to solve this only 2 to the power 3 by 2 and 10 to the power 3 by 2. Yes, is it clear? Is it? So if I write this, it's a magnetic field at P to the magnetic field at Q. It is equals to magnetic field at P, it is 2 to the power 3 by 2, and this is 10 to the power 3 by 2. So this could be solved as 2 to the power 3 by 2 multiplied by 5 to the power 3 by 2. This is divided by 2 to the power 3 by 2. This 2 has gone. This 2 has gone. And 5 to the power 3 by 2 could be written as 1. 5 to the power 1 into 5 to the power half. This is 5 root 5. This is BP is to PQ. I hope these things are clear. Is it clear? Is it? Yes. Yes. One more thing. You must took a ratio when you can observe that there are only a slight variation of distance at this place. So what you understand it at the very beginning is that I could write like this. It is something like this. Look at this. It's a mu naught I r square divided by 2 into bracket r square plus x square to the power 3 by 2. So in this case, my I is same, my radius is same, only the thing that is varying is x. So when only x is changing, what you need to do is you need to do this decision at the very beginning of this question, that be directly proportional to the r square plus x square to the power 3 by 2. Yes, and then you just took at the ratio. Yes, you will be directly on this slide, and time can be saved. And at this point of time, as well as in examination, time is our biggest asset. Yes, we cannot spend it at any cost. So the approach, this approach is not the incorrect one, that first put up the value of everything and find out the magnetic field at point P and then magnetic field at point Q and start doing it and start going to solve it. Yes, this is not the incorrect approach, but this is a time consuming approach. Yes, you must understand at class 12 students or at an RM students that we can go with this, and this will help me to save my time. I hope this is clear. Is it clear? Is it? Okay, great. Let's have a look to this question. It says that the wire shown in figure carries a current of 40 ampere if radius is 3.14 centimeter. Find out the magnetic field at point P. Okay, so what I need to do is, I know the value, I know the formula. It's mu naught I by 2r multiplied by theta by 2 pi. Now what should be the value of theta? Is it 90 degree? Is it? No. I need to consider this angle theta because this is the wire. Yes, so as I know that complete circle is of 360 degree, that should be a 90 is on this side, so 270 on the other side, should be 3 pi by 2. So let's fit the value and get the answer. It's a mu naught multiplied by I, that is of 40 ampere, divided by 2 multiplied by R. R is the 3.14, but again it's a centimeter, so that should be multiplied by theta, multiplied by 100, sorry, theta, it's a 3 pi by 2 multiplied by 1 by 2 pi. I hope this is clear. Is it clear? Is it? Great. So what I need to do is this pi and this pi has gone. The remaining term mu naught, it's a 4 multiplied by pi into 10 to the power minus of 7 multiplied by this is, look at this, this is 2 2s are 4, this has gone, and this is 100 into 10, it's 1000, so it's a 10 to the power 3 multiplied by 3 divide by 2 into 3.14. This is gone, this is 2 2s are 4, so this is equals to 2, 3s are 6 into, this is 10 to the power minus 7, this is 10 to the power 3, this is 6 into 10 to the power minus of 4 Tesla. This would be the answer. What was your answer? Is it same? Is it? Great. Well then, let's work for the next question. Do it quickly. You are doing nice thing. Keep it up. Let's look at the question. It says that a current I is flowing in a conductor shaped as shown in the figure. The radius of the curved path is R, and the length of the straight portions is very large. The value of the magnetic field at the center will be, okay, great. So what I need to do is I need to just divide this into different segments. This is first, this would be this circle, that means this circle which covers 3 of the 4th quarter. Yes, this is the second segment, and this should be the third segment, and I need to find out a magnetic field due to each one, and then I need to go with the vectors law of addition by finding out the directions due to each. So let's work one by one. It's a V1. It is something like this. At this point you require a magnetic field, and this is your wire. So if I stretch it something like this, then this is the case of theta is equals to 0 degree, and if it is the case of theta equals to 0 degree, as I know, it's a B1 should be equals to 0 degree, or B1 is equals to 0 Tesla. Now let's work for the B2. This is a circular loop. It's a mu naught by 2R multiplied by theta by 2 pi. Theta is 370 degree. Yes, this is a quarter which is 90, so remaining quarter it is of 270. It's a mu naught I by 2R multiplied by 270 can be written as 3 pi by 2 multiplied by 1 by 2 pi. This pi has gone, and this is equals to 3 mu naught I divide by, this is 2, this is 2, this is 2, 2 2s are 4, 4 2s are, it's an 8R. Yes, and as it is moving in anti-clockwise direction, it must be outside the magnetic field. This is 3 mu naught I by 8R. Now the last part, it's a third segment. That, let's look at this. This is the point P where you require a magnetic field, and this is the wire. We can say that this is the radius R. Yes, from this side the angle is 0, this alpha equals to 0, and this beta should be equals to 90 degree. So B3, that should be is equals to mu naught I by 4 pi R into bracket sine alpha plus sine beta, and that should be is equals to mu naught I by 4 pi R multiplied by alpha is 0, so this is 0, and sine beta, it's a sine 90 which should be a 1. Now what would be the direction? what would be the direction? You can use a right hand palm rule to evaluate the direction for the same. So if you go for it, if you go for the right hand palm rule, then the palm will represent it is that it is the outside the plane. Yes, so this is outside the plane. So now let's have a look that magnetic field due to the straight wire is 0. Magnetic field due to this, it's a 3 mu naught I by 8r, it is in the outside the plane, and even this is outside the plane. So B net should be is equals to B2 plus B3, because B1 is already 0, no need to write it. It's a 3 mu naught I divided by 8r plus mu naught I divided by 4 pi r. I hope this is clear. Yes, is it clear? So this could be written as it's a mu naught I. Yes, this is the same r. This 2 should be the same r. It's a mu naught I by 8 into r. So mu naught I by 4 into r could be taken as a common, and the remaining term, it's a 3 divide by 2 plus 4 mu naught I is the constant, and 1 divided by pi. So that could be written as B net should be is equals to mu naught I by 4r into bracket 3 pi plus 2 divided by 2 pi. This would be the outside the plane. This is the B net. I hope these things are clear. Is it clear? Is it? Great. So ready for the next question? Are you ready? Are you ready? Let's have a look. A very good question, a very, very logical question. Let's have a look. It says that magnetic induction at the point O. Yes, this is the point O. If the wire carrying current I is that this wire carries a current I, and it has been extended through the infinite, that means it is coming from the infinite and terminating over here, then I require a magnetic field at this. So this could be my first segment, this could be my second segment, and this is even extending up to infinite, that this could be the third segment. I hope this is clear. So let's just write down the value due to first, second and third, and then we are doing the same thing that we have done in the previous questions as well. So let's work for the B1. Yes, as I could understood that this is the semi-infinite wire, and for the semi-infinite wire I can have it's a mu naught I by 4 pi, let's write this as a distance r, multiplied by sine of 90 degree, because it has been coming from the infinite, and this angle, this would be the 0. It's a sine of 90 degree plus it's a sine of 0 degree. So it's this would be the 0, and this is mu naught I by 4 pi r. I hope this is clear. Is it clear? So let's just understood that suppose this is the x plane, this is x, this is the y, and this must be the z plane. So if it is the z plane, and the wire is coming from this, then this magnetic field will be in minus of j cap. I hope this is clear. Is it clear? Is it clear? Yes, great. Now let's work for the B3. And if I find out the magnitude of B3, it would be equals to the mu naught I by 4 pi r multiplied by again sine 0 degree, because it is being terminating over here and then reaches to the infinite. It's a sine 0 degree plus sine 90 degree. Again if you look at the direction, you are using the right hand palm rule, or you can use the virtual circular coil. Yes, so this will represent the magnetic field in the minus j cap. So it's a sine 0 plus sine 90 into minus j. That means it's a mu naught I by 4 pi r into 1. It's a minus of j cap. This is B3. And what about the B2? What about the B2? Let's suppose that this is Z, this is minus of k. Yes, if you use the right hand circular rule. So that could be written as B2 should be mu naught I by 2r multiplied by theta by 2 pi. And this theta could be represented by pi. This is equals to mu naught I by 2r multiplied by pi by 2 pi. This has gone, and this is equals to mu naught I by 4r. This would be the minus of k cap. Yes, so your two vectors are in the minus j cap and one vector is in minus k cap. That means for B net it should be a mu naught I by 4 pi r into minus of j cap multiplied by 2 plus mu naught I by 4r into minus of k cap. So that should be is equals to mu naught I by 2 pi r into minus of j cap plus mu naught I by 4r into the minus of k cap. Now I understood this is minus j, this is minus k. So if I want the value of this, I need to have this. Let's assume that this is the B1, this is the B2. So B net could be written as B1 square plus B2 square. You can put the value and get the answer. I hope this is clear. Is it clear? Is it? Are you sure? Can you do this? Can you? Great. Let's look at the next question. Yes, this is the formula. Yes, which we are deriving, and you need to remember this. But before this, let's have a look. What does it say? It says a coil having n turns is wound tightly in the form of a spiral with inner and outer radius A and B respectively. Inner radius as the A and outer radius is the B. When a current I passes through the coil, the magnetic field at the center, this is what I required. So first thing, do you understand the question? It is something like this, that this coil is there and this has been something like this. It's a spiral coil. The inner radius would be the A and outer radius would be the B. That is what they are saying. So if I understood well, that what I can do is that magnetic induction due to any circular coil could be written as B is equals to mu naught I by 2r. Yes, so this is the value of magnetic field at its center due to single circular coil. Now what I am having is I am having a coil having n turns. So what I can do is it's a B is equals to mu naught I by 2r multiplied by dn. Yes, well, how should I define dn? It's a, let's suppose this is r and this is the r plus dr. Yes, so this is from r to dr. From only this many segments contain, let's suppose, a dn number of turns. So what I have taken a small segment and where I'm going to derive it and then I'm going to integrate it for the complete situation. So how could I write the dn? What I need to do is that it's a total number of turns divided by radius b minus a multiplied by my thickness. It's a dr. So this is n upon b minus a into dr. So let's just put up the value. This b is equals to, b was the, it's a, if you remember this, it's a mu naught I by 2r into dn. So let's just replace the dn. It's a mu naught I by 2r into n by b minus a into dr. So what I need to integrate, I need to integrate this. So let's keep all the rest of the things at the outside the box. It's a mu naught into ni upon 2 into b minus a. You need to integrate it from a to b. So when I integrate it, it's a mu naught I a I n multiplied by 2 into b minus a dr by r. It's a log r. It's a log r. and while I replace the value, it's a log of b by a to the base e. This is the magnetic field. This is the magnetic field due to spiral circular coil. I hope this is clear, and you must remember this formula. You must remember it. Yes, this is very helpful. I hope this is clear. Is it? Okay, great. Let's look at the last question of this lecture. Let's look at this. Do it quickly. Yes, what does it say? It says that a ring of radius r is uniformly charged with a charge q, and if the ring is rotated with an angular frequency of omega, if a ring is rotated with an angular frequency of omega, then the magnetic induction field at the center is okay. So situation must be something like this. It is a ring, and this is having a radius of r, and it has been uniformly charged with q, and if the ring is rotated with an angular frequency omega, then the magnetic field at the center, so B could be written as mu naught into I divided by 2 into R. How could I have an I? It would be I is equals to Q divided by T. Yes, so I could be replaced by the I is equals to Q by T, and this T, we have an omega is equals to 2 pi by T, so I can write it's a T is equals to 2 pi by omega. So let's just replace all the required things. So this is B is equals to mu naught by 2R multiplied by I, and this is I is equals to Q by T, and this is mu naught by 2R multiplied by Q divided by T. This T is 2 pi by omega. So this is equals to mu naught into omega into Q divided by 2 2s are 4 pi R. This is the required magnetic field. This is the required magnetic field. It's a mu naught into omega into Q divided by 4 pi R. This is the answer. I hope this is clear. Is it clear? Great. So let's just wind it up this session over here. Yes, this is all about the Biot-Savart's laws application number 2, magnetic field due to charged arc on its center and on its axis. So this is all about the Biot-Savart laws. Yes, you need to revise it, you need to practice it a lot, because as we have discussed in the very first session, very first lecture of the Biot-Savart law, that no paper could be there without having a questions from the Biot-Savart law. This is very, very important. Please do it, go through it, at least have a 150 to 200 questions of Biot-Savart's law and their applications. Please do it. This is required, as we are on the second part of the physics of unit of class 12. Yes, this is what we are discussing with the magnetism session, and this is very important session to build up a concept as well as to have a good numbers on the competitive examinations. So please do it. This will help us. Thank you. Have a good day. Take care. Bye.